So I'm going to talk about concurrency in using coroutines in Python 3. My name is Rob Smallshire. I recognize quite a few faces in the room, so you know who I am already. Essentially, I'm an economic migrant from the UK to Norway, and where, together with this fellow in the second row here, we have set up a small consulting and training company called 60 North. And we do many things. Those of you who went to Austin's Elm talk this morning will have found that that's something we do now. But by and large, a large proportion of what we're involved in is around the world of Python. Helpfully, somebody has written a list of adjectives for this talk on here. So I have to promise to be boring, wrong, expendable, misleading, at some point tedious, irrelevant, unfindable, contentious, and incomplete. So let's see how we manage on that list. So my first professional exposure to working with coroutine concurrency in Python was about a year ago now, where we did some consulting work for a company in London, a startup company in London, and they're involved in a business called demand response for the electrical grid. And so what they do is they have customers who have large industrial electrical loads, which can be turned off. You can elect to turn those things off. So the canonical example is something like an ice rink freezer, right? If you turn that off for 10 minutes, you know, the ice rink is not going to melt. People can still go ice skating, right? But you can maybe provide, you know, a few hundred kilowatts of electrical power, which you can then resell to other people. So I was involved in a project for them, writing software in Python using the techniques I'm going to show you today, sitting on a small embedded board, similar to a Raspberry Pi, a thing called an Odroid, which communicates on the one hand with industrial controllers and power meters on industrial sites, and also communicates back to their central servers, which, based on the electricity spot price, decide whether to turn things on or off for their customers. So if all the lights go out and everything stops working, you know who to blame. As a result of that project, and informed on my experiences with that project, I am now the author, pretty much the sole author actually, of a thing called PySerial Async IO. Serial ports are something that a lot of people think are very old-fashioned and have been around forever. Anyone who's been involved in any embedded computing realizes that the entire world runs on serial ports. And they're a very, very important piece of hardware infrastructure. And PySerial is something that's been around for almost as long as Python, I think. And Async IO combines the asynchronous concurrency features in modern versions of Python and allows you to use those with serial ports. So that is real-world code that is out there in production now. I'll also just briefly mention that we are the authors of some Python books. If Python is new to you, who here programs in Python regularly? Right, so nearly everybody in the room. You probably don't need these if you've been using Python at any level, but if you do, you can use this URL token now and you can get a free copy. So let me just run you through the structure of the talk. I'm going to start by introducing some ideas and concepts before we get into the code. I mean, why are coroutines and Async IO in Python important? Why do we care? Why is it a good thing that they exist? Then, rather than going into using the new features in Python, I am going to recreate those features using the tools that we had before they existed from scratch. Essentially, I'm going to recapitulate the journey I went on when I was trying to understand this stuff, and that has been turned into a lesson. And I find that's a very effective way of building up from first principles, building up from stuff that you already know how it works, build something that's functionally equivalent to a large chunk of the new stuff in Python, and then we'll replace it with the real thing later in the talk. So then I'll move on to what is actually available in Python 3.5 and 3.6, the most recent versions. But not until the end of the talk will we actually get around to talking about I/O in the context of concurrency, which is, of course, one of the the driving reasons for doing this. So what is all this about anyway? Well, the problem is that computers are incredibly fast compared to I/O. I/O is very high latency. When we make a request to, or need to wait for some data, we tend to have to wait a very long time, in terms of CPU time at least. And so sequential programs without any concurrency waste resources just sitting around waiting for things to happen, okay? Now, these problems have been able to be solved for many years now using other techniques, multi-threading, where we have multiple threads of execution in the same program, or multiprocessing, where we just have multiple processes which communicate in some way and we rely on the operating system notion of processes. Obviously, threads and processes are very closely related things, and they come with actually pretty large resource overheads. I think on Linux, every thread has at least an 8 megabyte memory overhead. So, of course, when you get into dealing with thousands of threads, that all begins to add up. Perhaps more importantly than the resource overheads in computing terms is the cognitive overhead in just figuring out how all this stuff works, and just the difficulty in reasoning about highly concurrent, parallel threaded programs where there is inevitably at some point some mutable state. This is a particular problem in the context of Python because, of course, the Python interpreter itself is this huge blob of shared mutable state. And that is protected by the infamous global interpreter lock, which essentially prevents you extracting the potential power of your computer in languages like Python. If Kevlin Henny was here, he would call this the global interpreter bottleneck. So let's just establish a few definitions. And in particular, I guess the most important one is the difference between concurrency and parallelism. I'm sure most people in the room are familiar with these ideas. But essentially, concurrency is about dealing with multiple things at the same time, whereas parallelism is about actually doing multiple things at the same time. Okay, so concurrent tasks, their begin and end points overlap in time, although we're not necessarily progressing more than one of those tasks at any particular instant. Whereas parallelism requires hardware that is capable of physically doing more than one thing at the same time. So typically multiple cores or multiple processors or multiple machines. Some other words which are, I think it's important to nail down what they mean. Asynchronous. In this context, what we mean is we don't need to wait before proceeding. We can initiate some piece of work, and we don't have to wait for it to complete before we can get on with the next thing in the sequential part of our program. And of course, this is great because it makes the overall duration of our program execution shorter. Compared with the default, which is sequential execution or synchronous execution, where each piece of work must complete before we proceed to the next one, and of course the overall duration is longer. As someone who's interested in words, I find this kind of fascinating because to everybody else in English, synchronous means at the same time, right? And in this usage, we mean it strictly one thing at a time. So I think it's kind of interesting how we have made these words have almost the opposite meaning to what they do to the rest of the population. There are some refinements to asynchronous behavior. We can deal with callbacks or futures or promises, where essentially we start to make a synchronous task, and that from the point of view of the calling thread of execution, it returns immediately with the promise of some later result. And we know we're going to get that result eventually, we just have to wait around for it. We have to, and it will essentially call us back or signal us in some way when that result has become available. Another way of achieving the same thing is non-blocking behavior, which returns immediately without a result, maybe with a partial result, or even the complete result, But if we don't get the complete result, we then go back and we poll until the result we want has become available, assuming it does become available. So these distinctions become important when you think about how to structure your programs, as we'll see later. Of course, ultimately, when we think about how these things work at the operating system level, or in terms of multiple tasks, there's a distinction between preemptive multitasking, whereby the scheduler is in charge and it interrupts the tasks. And by and large, the tasks have no say in when they are interrupted. And of course, it's always at the most inconvenient instant, which means we have to do extra things to deal with the fact we could be interrupted at any moment, such as locking. Or there's cooperative multitasking, where each task voluntarily yields control back to the scheduler. Okay? So that's much easier to program with, because then we get to choose when each task yields. We can do that at the task's convenience, and as long as we do it frequently enough, the illusion of multitasking will be maintained. The problem is that uncooperative tasks, which don't yield frequently enough or at all, can hang the whole system. Of course, preemptive multitasking does require hardware parallelism, and even if you have one CPU and one core, you still need hardware parallelism, and the way that's done is with CPU timers, which are truly parallel bits of hardware inside our CPU. So when we're talking about coroutines today, this is very much the model here that I want you to have in mind, one of cooperative multitasking. So even though the underlying operating system we are using is almost certainly using preemptive multitasking to schedule the threads in your program, the kind of concurrency you're going to be doing in Python is very much cooperative multitasking. Does that make sense? So Async IO and the new tools in Python allow us to write asynchronous, concurrent, cooperative tasks. And I guess the big selling point of this stuff is it allows us to do it, to write our programs in a sequential style. Right? We don't have to get too hung up on the fact that multiple things are happening concurrently. And for a large part of the time, we can effectively forget about that, which is great. So in the next part of the talk, I am going to show you how to build a system using incorporating coroutines without using any of the new facilities in Python, just using functions and generators, which we've had for years. And in fact, you could make this worth it. I'm a big fan of Python 3, and I think Python 2 needs to die in a fire as soon as possible. That said, everything I'm going to show you in section 2 here, you can build in Python 2. All the pieces you need to do that are there. So to support this talk, we need to do some work. We need some tasks which will actually perform some work, some fairly trivial computations. We have a pact in our company that neither of us are ever allowed to use the F word when presenting. And so if you're not already familiar with it, this is called the Lucas sequence, which is very similar to the F sequence, but just has different starting conditions. So on the left here, I have a function called Lucas, and you can see that because that function contains the yield keyword at least once, that is what we call in Python a generator function. Okay, so when we call it, it will return a thing called a generator object, which is essentially an iterator, as we'll see in a moment. So on the right here, I've imported my Lucas function. I'm using a standard library tool called iSlice, which just allows me to take part of the sequence or part of the series returned by Lucas. So here I'm just taking the first 10 Lucas numbers. Yeah? Is everyone familiar with this Python at this level? Everyone comfortable with this? Because if you don't get this level of use of generators, then the rest of the talk might be a little bit lost on you. So That's the starting point. And the only reason we have these functions is because they just do some work. And we need some functions to do that. So the next thing I'm going to introduce is a very simple linear search function on the left here, which accepts some iterable series, and it also accepts a predicate function, which is going to return true or false. And so we're iterating over all the items in the iterable series, testing each one against the predicate, and if the predicate returns true, we've found a matching item, and we return the item. If we get to the end of the iterable series without having found a matching item, we raise a value error. Yeah? Very simple. So here I'm using my search function on the Lucas sequence, which of course is infinite, to find the first Lucas number with more than 6 digits, okay, which is 103682. So search is just a regular function, right? There's nothing exciting about it. It's one of the simplest functions you could write in Python. And it either returns a result immediately, or returns a result with return, or it raises an exception if it can't return a result. Very simple. What I'd like to do is take the search function and make it into a cooperative search, okay? Because with this version of search, when I call it, my program is busy searching until it either returns or raises an exception. There's no way to do something else at the same time. So to make it cooperative, what we need to do is just insert the yield keyword here. We don't need to yield anything. In fact, this is shorthand for yield none, in the same way that just return in Python is shorthand for return none. So we're just yielding. It's exactly the same function otherwise. And just to remind us that it's a different beast now, we're going to give it a different name. I'm going to call it Async Search. Okay? So let's see how Async Search behaves. So I'm going to import it and my Lucas generator. And I'm going to make the same call I did before. So the question is, what is G? Is G the number we're looking for, or is it something else? Well, because async search is now a generator function, because it has at least one occurrence of yield in it, G is now not the answer. G is a generator object. So it's a deferred. We've deferred the computation here. Now, generator objects in Python are iterators, and the way in Python 3 we iterate an iterator is by passing the iterator to the next function. Okay? So we can iterate G, and because each time we iterate, we run up to the yield and return none, and because the Python REPL doesn't display non-results, each time we do next G, it doesn't print anything out. Okay? So all we've done is run another iteration of that loop. So we need to call next G again. Still nothing. And next G again, still nothing. I could have you here all day. This is how I've extended the talk to 90 minutes, right? So this was a 15-minute talk, and it's now a 90-minute talk. The really interesting thing here, which is not immediately apparent when you're doing this, is that we can do other stuff at the same time, right? My search function is running. Okay, it's suspended at this instant, but it's in progress, right? And in the middle of me searching, I can print hello world, right? I can do something completely different, okay? And then I can carry on searching, okay? So this is overlapping tasks which are being progressed at the same time. They overlap in time, but it's not parallel because only one of them is being advanced at any particular instant, right? And that is the basis of how concurrency with coroutines works in Python. I mean, that, in its essence, that's all there is to it, right? Everything else is just convenience built on top of that behavior. So, who remembers what happens when iterators in Python are exhausted? Which is called? stop iteration. Right. Okay, so eventually we get a stop iteration exception. Now, what most people don't know about stop iteration is that it can have a payload. Right. And so what happens is when we eventually hit the return here, because this is a generator function, so normally with generator functions, you just fall off the end of the function, right? And the Python runtime machinery says, oh, this is a generator function, I'll raise stop iteration. The for loop or whatever you're using to iterate intercepts that, and you never see it. Right? Here, because I'm using next at a lower level of abstraction, you get to see the exception happening. Okay? Now, when you return from a generator function, which is not something you normally do with a value, Python wraps up the return value and puts it as the payload of the stop iteration exception, which is reported here. Right? That makes sense? So Python is infamous, I think, for abusing exceptions for this particular use case. But it's turned out to be kind of handy because we realized that you can smuggle information out of your generator functions inside the exception object. So async search is a very different animal to the search function, just because we put that yield in there. It's a generator function. Calling async search always returns a generator object, and the search progresses when we iterate with next. And the final result is returned in the stop iteration exception payload. So, who's learned something about Python so far today? Great. I'm done now. Yeah, there are no stupid questions.
What if you substitute return item
with yield item, then my next function would be returning that value. Yeah? If I... Yeah, it would yield it. Well, no, then it would yield all of them. Then it would yield all the matching items. At the moment, it exits at the first one it finds that matches the predicate, right? With your...
Because the predicate says logger with 10. It would be exactly equal 10. That would yield nothing to the next step.
Right, and we might run forever. So we're going to see a very similar function to the one you just proposed in a few minutes, yeah?
Those four songs like me are still on Python 2.
Yeah.
I did implement coroutines for us. You can't do a return in the generator.
Can you not do it in Python 2?
So
You can raise stop iteration?
a magic thing which says, I'm done now.
Okay.
Coroutine machinery is going to, oh yeah, that's what it is.
Can you rate, is that because stop iteration doesn't have a payload?
It just says not allowed, it's that thing just goes, no.
Okay. You could try raising stop iteration. Yeah. There's also another exception. Yeah. Well, that's a good point, though. There's also another, well, really, you should just move to Python 3, and then all your problems will go away. But, and we can help you with that. But, there's also a generator exit exception, which you might be able to raise to do the same.
But like I say, we want pretty syntax in our coroutines. So
Yeah.
yield value is slightly prettier than base.
Yes.
Value, in my opinion.
I would completely agree.
Return would be the nice one.
Yeah.
Return underscore would be an option,
Yeah. Great, you're asking excellent questions, which mean you understand what's going on. Okay, so the next level of sophistication here is to, rather than dealing with these generator objects, which are just iterators, we'll make them a little bit more pleasant to deal with by wrapping them up in a task. And a task is a very simple thing. It accepts a coroutine, or object, essentially a generator, and we give each task a unique ID. So those of you who don't know Python very well, this thing is like a static variable in the class. Okay, and we increment it. We assign the current value of that to an ID for the task, and then we increment it so that we get task 0, task 1, task 2. So task is an extraordinarily simple thing. Now we need a scheduler, which actually also turns out to be a very simple thing. So here's a scheduler for running tasks, and it consists of a collection of tasks in a deck, double-ended queue, and 2 dictionaries in which we can store the results from tasks which have completed successfully, and we can store the exceptions from tasks which have not completed successfully, failed in some way. We have a method add, which allows us to add a routine. And all this does is wrap up the routine in a task and append the task to the queue, and then return the task ID. Okay, it's a very straightforward thing. Then we have the meat of the scheduler, which has a certain elegance to it. In spite of all the exception handlers in here, it's conceptually quite elegant, I think. While there are tasks to run, get the next task by popping it off the queue, try to run it with next. That iterates the task, right? So pass it to next. That will return a value which we're expecting to be none, right? If calling next raise stop iteration, we know the task is complete. So then we get the value from the stop iteration exception and stick it into our dictionary of task results against the task ID. If we get some other exception, something has gone wrong, and so we get the exception object and stick it in the dictionary of failed task errors against the task ID. Else, who knows about try else in Python? Who can explain try else in Python, right? So you end up in an else if the try succeeded, okay? So if next worked fine, we come in here, we assert that yielded is none, because we're only, if you ever yield something other than none, that's a mistake, that's a programming error, right? You should never have done that, so an assert is appropriate there. And then we know we've iterated successfully, but the task is not yet complete, so we stick it back on the other end of the queue, and it just goes around again. Okay, it's an extraordinarily simple thing. Okay, that's a complete task scheduler in one screen full of code in an 80-point font. So, very simple thing. Everyone understand that? Yeah. So let's try to use it. We'll import my scheduler. I'll instantiate a scheduler, and I will add my async search task to it. And then I have a method. We start the scheduler running, which does the thing with the queue I just showed you, and it just iterates and runs the task, prints out a message on each iteration. Eventually the task raises stop iteration. We intercept that, get the result, and then we can pop the result out of our dictionary, and we're done, right? It's a very simple thing. So obviously, it's not very exciting with one task, is it? So let's do it with 2 tasks. Here we just do 2 searches concurrently to completion. So you see I'm getting the task ID back here. So this is, you can see I did this in the same session, because last time it was task 0. Now it's task 1 and task 2. Run to completion again, and now you can see we get alternation here. Run task 1 a bit, run task 2. Down it goes. Task 1 completes first, we get the result. Task 2 continues running, it's now the only task in the queue, and then a few iterations later we get the result from that, and we're done. Okay? So it's a very, very simple thing. We have implemented concurrent tasks from almost nothing, leaning heavily, of course, on the generator machinery in Python, but it's a very simple thing. Get the results out. Okay, so we're generating Lucas sequences and we're searching Lucas sequences, but I want something that does a little bit more work, right? So here is the world's least efficient primality testing function, and it's deeply in my interest that this function is not very efficient, because the objective is not to find prime numbers, the objective is to do work, right? So this is great. The fact that it's not very efficient is okay, and obviously it can find it can determine that 12 is not prime and that 13 is prime very quickly, but when you start throwing numbers like this at it, it takes a significant amount of time to go through, because of course even the square root of this number is quite a large number, and Python is not a fast language, and that takes a lot of time. So there's that is prime function. You don't need to understand how it works. And here is this is another function, async print matches. This is very closely related to the search function, except now rather than us returning the first match, we're printing every match, right? So we just test against the predicate. If it matches, we print it. And we just run forever. So this will go on for as long as the iterable series. Okay? So let's try this. So I create my scheduler, add async print matches with the Lucas sequence and my isPrime predicate. So now we're looking for prime Lucas numbers, right? And when we run this, you can see that we're finding the prime Lucas numbers, and we can see which Lucas numbers are not prime because we just iterate without printing on those occasions. And this runs and will run and will run because, of course, it's an infinite sequence. But the point is now the point is that we're now doing quite a lot more work computationally than we were doing previously, because on each iteration, that is prime function is having to do increasingly more work as we go down this list of ever bigger numbers. Here's another simple task, repetitive message. So you can see how this one works. We accept a message, just a string, and some interval in seconds, and we go into an infinite loop here. We print the message, and then we basically just spin in this loop until the current time has reached the reached the interval time, and then we break out of the inner loop and then print the message again. Right? So this will never exit, because the break only gets us out of the inner while. There's no way out of the outer while. So this is an infinite running task. It just prints a message every n seconds. To make this cooperative, we need to put the yield in there. Okay? Otherwise, it will just block. So I put the yield at the bottom. There's a bug here. What's the bug? This is quite subtle. That is the bug. All right, it really matters where you put the yield. So let me just rename this to async. If interval seconds, you almost said this exactly. If interval seconds is very small, the coroutine will never yield and will hold the system. You have to put the yield there, right? We just have to reorder the code. It's really important when you're doing these things that your coroutines either return the result immediately or they yield at least once. Otherwise, they are blocking. Okay? So either, if you can't produce the result there and then, yield, and then come back and do the result, do the computation later. So it's really important to get the yield in the right place. It took me a while to figure that out. But that's general advice that applies to any coroutine you write in Python. So let's try this. Create the scheduler. So the first task is going to be a repetitive message. I spend a lot of time in airports, so this phrase is, I have an entire section of neural circuitry responsible for filtering this out. And then our second task is async print matches the prime Lucas numbers. Okay? So we're expecting it to print unattended baggage will be destroyed every 2.5 seconds, and to print the prime numbers out as it finds them. Right? So off we go. We get a message after a couple of seconds. That's what we expected. And now you can see it's running task 0. but we're not getting our message. Right? We should definitely have had a message by now. Okay? And if we wait long enough, it will eventually print the next prime Lucas number, and then it will print the unattended baggage message. There we go. Yeah? So the problem here is that even though async print matches, our search function is non-blocking, the is prime predicate function we've passed to it is blocking, and that can take a very long time to execute. Yeah? And so when the numbers get big, it takes a long time to figure out whether they're prime, and while it's figuring out whether they're prime, the other task is deprived of an opportunity to run, so it doesn't run. Okay? So you have to be very careful about whether your functions block. So here's a guideline, or a rule if you like. Basically everything you call transitively from a coroutine should be non-blocking. Yeah? Because otherwise you're going to run into this situation. So coroutines are contagious to callees, right? If you want to do some work in a coroutine, you probably better make it a coroutine. There are other ways of being non-blocking. You could use a thread, but given the way we're approaching concurrency here, using another coroutine is the right thing to do. So coroutines are contagious to callees transitively. So everything down from your coroutine is probably going to be a coroutine. Fine. We know how to deal with this. We can take our isPrime function. So here's the original on the left. We call it with a number, it returns a bool. Here's the concurrent version. We know what to do. We just added that yield in there, makes it into a generator function. Now calling it returns a generator object. Yeah, so all I've done is added the yield there in the loop. But now, async print matches thing can't just call the predicate function. It has to iterate the predicate function because it's now a generator, right? And the way in Python 3, at least, when was yield from introduced? Like 3, came with 3, right? Yeah. So the way you iterate another generator is with yield from. I mean, you don't need yield from because you can replace every occurrence of yield from with another for loop. Okay, but then your code gets quite messy. So now we need to do yield from on our predicate function, which is a little bit weird. That's why we don't start with this code, right? We build up to it. Because we know that predicates return true or false, and suddenly I'm saying you have to iterate it. So now we've modified our print matches. And what's really interesting, and this is significant, is that I call this a bare yield. That's a term I've invented. It's just a yield which is only there for the purpose of yielding control, not to yield a result. When you do this, as soon as we yield this thing, yield from this predicate, we no longer need this bare yield here, because this predicate has a bare yield in it, which will ultimately yield to the scheduler. Okay? So each task only needs one bare yield in it. It needs at least one bare yield. Okay? You can't do this with just yield from. But this essentially becomes unnecessary. If we have this in here as well as this will yield to the scheduler twice per loop rather than once per loop. Okay? So as long as there's a yield at the bottom, a bare yield at the bottom of the call stack, we can get rid of any other ones that we had further up the call stack. That took me a while to realize, and it turns out to be very, very important and very useful. So here's another guideline, rule. Everything that calls transitively to a coroutine must iterate the generator or the coroutine. So not only are coroutines contagious to callees, they are contagious to callers. Okay? So this viral property means that very soon, almost your entire system is going to be written in this style of programming. Now, that isn't strictly true. As long as the things you're doing with regular functions are effectively almost instantaneous or fast enough that they're non-blocking, then you can call them. But you cannot afford to have any long-running behavior in regular functions. They have to be coroutines. So if you have a system in Python which is not written in this style, I don't think you're realistically going to refactor your way nicely to this style. Well, you can, but it's not going to be an easy process to do that. It's something that you set out building the program this way from the outset, and then everything will be much easier. Okay. So everyone's familiar with extract function or extract method as one of the second most simple refactoring after rename. So we can do an extract coroutine refactoring, which is basically the same idea. So our async repetitive message has this block of code in it here. Okay? If you had to give a name to that code in that rectangle, what might you want to call it? Sleep, right? I mean, that's what it does. And that makes sense. Repetitive message involves printing the message and sleeping in a loop. So we'll refactor async repetitive message to print the message and then yield from async sleep, which will be the extracted code. Very straightforward refactoring. Of course, because we're extracting a coroutine, we have to yield from the coroutine rather than just calling it. Now, this refactoring turns out to be very important. Async sleep is an interesting function. It always yields at least once, because we fixed that bug in it. And async sleep 0 yields exactly once, which is a useful property to have. So because async sleep 0 yields exactly once, we can replace every occurrence of bare yield in our program with async sleep 0. Yeah? Which is quite, it's not an obvious refactoring, I'll grant you, but it's an important one. So here's all the other code we've had so far. Async is prime, async search, async print matches. We've got a bare yield there and a bare yield there. We can convert those to yield from async sleep 0 without any change in the behavior of the program. Okay? We're actually making it do a bit more work, but so what? It's a useful thing to do. And what this means, and this is really interesting, is that if you do this refactoring, now your whole program only needs one bare yield in it, which is the one inside sleep. Okay? That's the only bare yield you need. Because if you want to do bare yields, you just call sleep 0. And being able to localize that yield in there is important, because that is the only place you then yield control to the scheduler. Okay? And if you think about sleep, how sleep works in operating systems as well, right? That's an opportunity for a context switch, okay? And we're using it exactly the same way here. Yeah?
So, if you, in that code you just have, you're sort of back to the world where you're yielding multiple times per iteration again, is that right?
Sorry?
In this code that you've got here, you're sort of back to the world of yielding multiple times per iteration, is that right? When you're calling the yield from async sleep in multiple places.
So if I have async search calling async is prime,
And just both doing the yield from async sleep.
let's see.
I mean, which isn't necessarily a bad thing, but
Yeah, that is true. Yeah, there are now multiple yields back to the scheduler. In that. Yeah, that's correct. So here we go again, after our refactoring. There's our unattended baggage message and our prime Lucas numbers. Let's run to completion. And now we get the message every 2 seconds, quite nicely, and occasionally we get a new prime number. So I promised you at the beginning that parts of this presentation would be tedious. Did I not? So I think we should wait for the next prime number. I just want you to share the pain of all the airports that I've been in. It is a 90-minute talk. We're halfway through.
We have time for a question while it's running.
I would think so.
So this may be quick and I question, but is this running live or have you done some sort of screen?
These are videos.
Videos.
Yeah. I will do some live demos later. Oh, there we are. Right, we can move on now. Great. Okay, so I have just built from Python generators a cooperative multitasking system using a very naive, simple scheduler. But it works, right? I mean, it has all the right qualities, okay? And obviously, for a real system, there's more you'd want to put in there, but it has the basic features you would expect. Now, in the next part of the talk, I'm going to move on to the actual features that you get in Python 3.5 and 3.6, which is the most recent version. If you're doing concurrency in this kind of type of concurrency in Python 3.4, what I've shown is pretty much how you do it. You have to use yield from to yield from the coroutines. The new stuff in Python 3.5 is essentially syntactic sugar on top of what I've just shown you. So underneath, it's all still yield from and yield. There's just some new keywords to make you think in terms of tasks rather than in terms of iterators, right? Just to conceptually separate those in your mind. It's almost all for the benefit of the developer. It makes no difference to what's actually being executed. So this code that I've put together here has been very carefully designed so that I can actually mechanically refactor it from my version into legitimate Python 3.6 code. Okay, so watch carefully. That's all the code I've shown so far. You understand all of it. I'm going to mechanically refactor it into 3.6 code. First thing, every time I've written def async foo, we are going to use async def foo. So async is a new keyword in Python 3.5. So let's do that refactoring there. So now we have async def instead of def async underscore. Now I need to import the library which handles all this stuff, Async IO. So we'll import that at the top there. Now I can replace calls to my sleep function with Async IO's sleep function. Okay? So rather than async underscore sleep, we're going to do async IO dot sleep. Okay? This is important. What we're saying here is essentially the sleep function is provided by the scheduler. Right? And remember, that's the only place we need the code that actually yields to the scheduler. Okay? So we'll do that. Now I don't need my sleep function, so we could delete that. And then finally, every time we had yield from something, we do await something. So await is pretty much just a synonym for yield from. Okay? And there we are. We have beautiful Python 3.6 code using somebody else's, using their scheduler rather than my scheduler now. So of course we can now delete my scheduler as well. So, yeah? All right, go ahead.
So not that you need to rationalize Python's decisions, but why do they require the async keyword rather than, so like Python determines whether you have a function or a generator.
Yeah.
Why do they not infer that it's an async routine based on whether it does async sleep or
With the await keyword. Yeah, that's a good question actually. In Python 3.4, you need to use a decorator on your coroutines. It's slightly more involved than what I've shown you here, and that's because they are another way of, a slightly different way of approaching this is that when you first create a coroutine, you want to run it up to the first yield, and they have a decorator that does that for you, right? And the await stuff works in the same way. It runs it at least up to the first yield. Whereas with a normal generator, it doesn't run at all until you first call next on it. Yeah? So essentially, what the extra machinery is doing is calling next at least once behind the scenes. Yeah? So it is slightly different to what I'm doing, and I think we see that here because even though I promised you this was a refactoring, you do get slightly different behavior because it's iterating the functions earlier in this version. So before, on my version, I think we got this message twice before that prime, and in this version, you only get it once. So it's not strictly a refactoring because it's a completely different scheduler. Yeah? I'm not going to make you wait this time, unless you have questions. Of course, yes.
So I wrote a coroutine on my own in Python 3.4,
Yeah.
where I basically have two cooperating coroutines. One yields values to the other one sends stuff back into it. So I actually communicate.
Oh, you use send on the generators, yeah.
But I basically communicate values between
Right.
the coroutines, whereas here you pretty much only use yield to yield control back to the scheduler, and there is never any value being transmitted with that yield.
No, that's right. Yeah. So that's the stuff using send on generators is a kind of different style of programming coroutines.
Yeah.
Yeah.
So as far as I can see, there's no way you could make use of a yielded value inside the system because the yielded value would go back all the way to the scheduler.
Yes, that's correct. Now in 3.6 we have async generators, which are there to solve that problem. Okay?
So then you
Because so the problem here is that they've overloaded the notion of iterator in Python to mean 35 different things. Yeah? And sometimes, you know, we need to be more precise about exactly what we want to do. So now in Python 3.6, we get async generators as well.
Okay.
So, which solve that problem of.
I guess what my real question was is that it seems that this coroutine concept and yielding back to the scheduler has sort of hijacked the yield mechanism in Python.
Oh, yeah, it has, totally, yeah.
So you would need.
Yeah, and that's another reason why they've introduced the new keywords, is so that they could keep yielding in its original sense for yielding progressive results. Yeah? And then we can have a different mechanism and set of keywords now for doing concurrency.
Does that mean that the await keyword, which is basically just yield from, will do extra checking to make sure that what you're actually yielding from doesn't actually yield results, which would make sense in an async?
Yeah, it will give you an error if you try to do stuff like that. Essentially, the runtime system that is inside the Async IO machinery does quite a lot of checking to make sure that you're not doing the wrong thing. Right, exactly, yeah. Yeah.
Are async routines allowed to call non-async routines, or once you're in async?
Yes, they are.
They are.
Yeah, but of course, if they block or take a long, just take a long time, you have hung the whole system. Sure. Yeah, so it's entirely up to you to not block or just do everything quickly. Yeah, there's no checking for that. Yeah, so I don't have an example of that in here, but we have some code for a course we run, which has a large domain model in just regular Python without any of this coroutine stuff. And then we have a Async IO-based REST API sitting on top of that. And that's just fine, because all the domain model calls are extremely quick. Yeah, but if any of them took any time, we would then need to either make them into coroutines or do them in another thread or something. So essentially, they have to be non-blocking. Okay, so we've built a program using my own scheduler. I've transformed it into one using Python's new scheduler and new keywords. But Async IO brings a lot of other machinery and tools which are essentially layered on top of the stuff I've already showed you. Tasks, and we'll get onto things like futures in a minute. Yeah, so coroutines implement tasks. Coroutines await other coroutines rather than yielding from. The event loop schedules concurrent tasks. Tasks must not block, which is the question you just asked. Whenever we await, that's an opportunity for a context switch. And if we ever wanted to yield control without needing a result, we just want to yield control to give the scheduler a chance to run another task. The way you do that is await async IO sleep 0. Okay, just a word on terminology, because I find this, it's not confusing, you just need to be aware of it, because people aren't very precise in the language they use, and I think the more precise you can be, the better. The language that the Python documentation uses is pretty consistent, but not completely consistent on this. This is a coroutine, it's just some code, okay? When you call that, what you get back is a coroutine object, okay? And so the thing on the left is callable, it's code. The thing on the right is the code plus its execution state at that moment, right? Because it's naturally an executing thing. So I just like to be clear about the distinction between coroutines and coroutine objects. It's easy to get muddled up. Okay, so let's look at some of the other things that Async IO gives us. And in particular, futures is one of the other tools we get. So a future encapsulates the idea of a potential result, okay, or an error. And in this code, we are going to use a future to monitor the progress of a search function. So here's my monitored search function, which just wraps my other search function. And you can see in here, I'm awaiting my regular search function. That this monitored search accepts a future object, which we'll see in a moment. And then when we're done here, if the search failed, we set exception on the future, or if it was successful, we set the result on the future. Okay? And the reason we do this is then in some other task, we can ask that future whether it has a result yet, or has an error yet, or is it unfinished. Okay? So this is a monitored search, which uses the future to signal whether it's finished or not. Here's another task which monitors the future, so it accepts the same future, and every interval seconds, we ask the future whether it is done yet. Okay, so that will just return true or false until it's done. And then down at the bottom here, I have to create the future object, which I'm then going to pass to those two tasks, because they're going to share the same future instance. So I have to get hold of an event loop. I ask the event loop to create the future. I create my monitored search, which is just like the regular search, except it also accepts the future object. And that's the coroutine object I get when I call this. I then have to create a task from that. So that's wrapping up the coroutine in an async IO notion of a task. Confusingly, create task in async IO doesn't just create the task. It creates the task and schedules it for execution. Okay? So when you call create task, it's actually going to start running that task, which I find the naming a little odd there. Then I create the monitor future task and tell it to pull the future every 1 second, and then we run until complete. And off we go, and it's printing waiting until we get the result, and then the program exits. You see Async IO has some diagnostics in it to tell us that actually when we finished and wrapped up, there was still a task running that didn't exit cleanly. We'll fix that problem in a minute. I find this very confusing working with Async IO. You know, you read about futures and you think, well, how should I create a future? I'll call the future constructor. No, you shouldn't do that. You shouldn't call the future constructor because there's a factory function on the event loop which does this for you. Why? Because there are different types of event loop, right? There's a Windows proactor event loop, there's a Windows reactor event loop, there's some Unix-y event loop. You can make your own event loops. So if you want your code to work with some arbitrary event loop, then you should never go around creating futures yourself. You should always ask the event loop to give you a future, because then it can specialize how that's implemented. Yeah?
So in some languages, when you go to evaluate a future, if it hasn't been evaluated yet, you yourself go evaluate it. And in this case, that's not really happening, right? The future is really more a meeting point between two separate tasks.
Yeah.
As opposed to an opportunity to take over the work. Is that right?
Yes,
Yeah.
correct.
Thanks.
Then we have a task. So I've already created quite a lot of tasks already. We just haven't looked at what a task is. There's a really cryptic, I find it quite a cryptic statement in the Python documentation that says a task is a feature which wraps a coroutine. And at some level that statement is obvious, but at another level I find it very awkward to understand what it actually means. So then I have to draw out a little diagram of what does that mean. And basically it boils down to this, that a task is a feature that wraps a coroutine. So actually the statement is completely accurate, right? But it's not until I drew this picture for myself that I really understood what was going on. So really a task doesn't add anything to futures except coroutines. I think this is a really bad use of inheritance in the standard library, because it never, if you have a task, it never makes sense to call set result on that task, right? Or set exception on that task. That's just always the wrong thing to do, okay? So in C++, of course, these would be like protected or something, and that would be okay, but we don't have that in Python. So I think this is a really bad design, but it's going to be there forever now. We're just going to have to live with it. Okay. What am I doing here? Yeah, so because a task is a future, we don't actually need to create the future. We can monitor the task itself, okay? So that's basically what's going on here, monitor future with the search task. Even more confusingly, when it comes to creating tasks, you should never call the task constructor for the same reasons I just said for, you should never call the feature constructor. That's why we have the create task factory function on the event loop, which is a better way. However, even this is not the preferred way. The preferred way to create a task is to call ensure future, right? This took me about 4 weeks to grasp that this is the right thing to do, okay? And there are lots of Stack Overflow and mailing list questions about, what is the preferred way to create a task? And eventually I figured out that this is the right way to create a task, because ensure future does call create task, okay? If ensure future is a bit smarter, it's a bit more general. It doesn't just accept a coroutine, it accepts any awaitable. That's a new idea in 3.5. So it's a bit more general than create task, and it's also idempotent. If you pass it a task, it doesn't wrap it up again in another task, it just gives you the task back. So it's a bit smarter about what it does. But yeah, so I just put this here because I just want to share the knowledge that when you want to create a task, you need to call ensure future, which is totally non-obvious to me. Yeah, so in spite of its confusing name, it does actually return a task. So I just modified my code over here to use ensure future to create the tasks. So I get a search task and a monitor task, and I run the search task until complete. Of course, the behavior of the program hasn't changed, and I still have this problem with the monitor task not being complete, still running when the search task completes. Yeah, I haven't given all the tasks opportunity to finish. The way you deal with that in Async IO is to use Async IO gather, which enables you to create a future which waits on multiple tasks, okay? So eventually you have to boil all this down to one thing you can wait on, and you can do that with gather. So here I'm just gathering my search task and my monitor task, and then I don't have a slide for it, but then that error goes away. Okay, let's talk a bit about event loops. So I've been using the event loop, which essentially encapsulates the scheduler in Async IO, and I'm going to show you the public API for the abstract event loop class. Okay? So it's got quite a lot of functions in it. And I've tried to group them here into groups reflecting different types of things they're doing. So we've got some basic functions at the top, many of which you've seen in my code already, which basically start and stop the event loop, get it to run tasks, ask it whether it's finished working, shut it down. Then we have some functions for just scheduling callbacks. So I can pass any regular, not a coroutine, but just a regular Python function into these things and say, call this function soon at your convenience, or call it later, or call it at a specific time. So we can get the event loop to do those things for us. These are the factories I've told you shouldn't use, so you can ignore those. There's a bunch of configuration stuff in here which you really need. But we're not finished with the event loop API. There's a whole bunch of functions in there for controlling error handling behavior, so what happens when things go wrong, exception handlers. There's some diagnostic stuff in there. There's lots of diagnostic information in the event loop which you can turn on and turn off, and logging and things. We can deal with other asynchronous things that happen in our world, like operating system signals. We can add signal handlers. Sometimes when we do need to deal with blocking code, sometimes we do need to deal with blocking code that isn't a coroutine. The event loop gives us some ways of doing that as running executor, and that is capable of running a blocking function in another thread under the control of the event loop, or even another process under the control of the event loop. So that takes away some of the complexity of dealing with some blocking tasks that you may need to deal with. But we're still not done with the abstract API. We have low-level socket operations in the abstract event loop. So this is pretty low-level stuff, isn't it? Even more, this is in the same interface for the base class. We have all this protocol-based stuff in here for TCP and UDP servers. We can create connections, datagram endpoints, Unix connections. I'm not sure what happens. I'm not sure how you subclass create Unix connection when you're implementing the Windows event loop. I have no idea, but there it is. This just reinforces in my mind the fact that the people behind Python really don't understand object-oriented programming. But there we go. That's just how it is. I'm being unfair and I'm being facetious. Yeah. No, yeah. Yeah. Yeah, I don't understand either, but that's how it is, and we're going to have to live with it forever. So. Yeah. On his own, I think that was the problem. Right. Exactly. I think that's what's happened. Is basically anything that could possibly block has ended up in this API. So we can watch file descriptors. We can connect to pipes. I think there's even more. No, but
how do you add something that I've got a stuck welly, right? So I need to block on a stuck welly. How do I add that? Because there's so much everything else that might possibly want to be blocked well within that API.
Right.
Can you give examples of how you would add your own blocking?
That's not a problem That's not a problem I've run into yet, because I've dealt with serial ports, which are file descriptors. So I haven't had that problem. You can subclass this and make your own event loop, but of course the problem is it's going to force you to implement 300 functions, which you probably don't care about. So anyway. So the question is, what's all this stuff doing in the event loop? Which is a good question, right? which you've just asked. Why is all this stuff here? So let's try to answer that. Basically, it's there because it's blocking, right? And the event loop needs to know about things that block, that we can wait for. So the scheduler I showed you earlier, my own little toy scheduler, is just very simple, round robin. We just do the tasks in order and we go around again. And occasionally tasks are completed and we remove them. But it's very, very simple. Of course, if the scheduler is aware of things that can block, right, it can be smarter about the order in which it does stuff, right? So here we have some task here, 6, is waiting on some I/O. And we go around. Because it's waiting on I/O, we don't execute it, we skip it. But then data becomes available, and we can immediately go back and execute that on the next opportunity, right? Which reduces the latency then for dealing with that data that's just arrived, right? And then we can carry on doing some other tasks. Maybe that one blocks, but then later the data becomes available. We can go back and get it almost immediately. And of course, this is how Async IO is able to allow you to write systems which have relatively low latency behavior when it comes to dealing with I/O, because as soon as data is available, the scheduler can go and deal with it. That's also why all this I/O stuff is in the scheduler, because of course it needs to know about that stuff. It needs to know about select or epoll or whatever the Windows equivalents of those things are. Okay, so there's a whole stack of abstractions in Async IO. Everything ultimately is based on, really on generators, as we started out with at the bottom here. So suspendable, resumable functions, and that's what a generator gives us. On top of that, we layer tasks, which are basically a coroutine and a future. Async IO then gives us a thing called transports on top of that for moving data around over blocking channels. On top of that, it layers a thing called protocols, which is a callback-based API for dealing with blocking data. So it will call us back when data is available. I'll show you an example of this in a minute. And then on top of that, it layers a thing called streams, which remarkably are now coroutine-based again, right? So we have essentially coroutines at the very bottom of this and coroutines at the very top. And they're being used to represent things at very different levels of abstraction. But there's this whole layer of, this whole tower of stuff that you need to get to grips with. And you need to understand quite a lot of this stack to use the stuff higher up in it, I've discovered. Because if you don't, when things go wrong, you think you're doing some stream-based thing, and suddenly something happens in a transport, and you're like, oh, what's a transport? So it takes a while to get to grips with all this. So I'm going to show you a couple of examples just in the last 15 minutes or so of some actual code that does something vaguely more useful than what we've shown so far. It's going to be a little chat server. And just to go back a slide, the chat server I'm going to show you now is written at this level, the protocol level. So it's callback-based, okay? And the callbacks it deals with are connection made, connection lost, and some data received, okay? That's basically the 3 callbacks it knows about. So here's my chat room class. I accept an Async IO event loop. Because only one of my tasks is progressing at any time, I can have mutable data. I can have shared mutable data, and I don't need to lock it, right? Because I know that only one of these tasks is ever executing concurrently, okay? So this is where a lot of the complexity of concurrent programming melts away, right? Because you know that only one thing is happening at a time, as long as you think reasonably carefully, you can get away with shared mutable data. So I have a dictionary here that is going to map the usernames of people in this chat room to a transport object, which is an Async IO thing, which enables me to read and write data from that connection. In here, on the event loop I call create server, that returns a TCP server object. And that server will call this protocol factory for every new connection. So when someone connects to the chat room, it will call this thing and create a new protocol. And the protocol will have a reference back to the chat room. I'll show you the protocol in a minute. Then we have functions for registering new users. So we check that the username hasn't already been taken. If it hasn't already been taken, we register the transport which connects us to that user over the network against their username and broadcast a message saying, hey, someone's arrived in the chat room. Similarly, when they leave, we take them out of that dictionary and send a message saying that someone left the chat room. And then broadcasting messages is as simple as iterating over all the users and writing to the transport for that user. So we have a collection of transports, one for each user, and we just write a message to each transport, and it gets sent out over the network to all the users. The protocol is the thing that implements the callbacks. So we inherit from Async IO protocol, and we have a reference back to the chat room. And the three callbacks are here: connection made, data received, and connection lost. And essentially, the protocol mechanism in Async IO runs this simple state machine. For each connection, connection made will be called exactly once, data received will be called as many times as necessary, and connection lost will be called exactly once. Okay? So it just goes through that process. Every time we get some data, it's just raw bytes. We have, there's no, it's not any higher level than that. It's up to us to convert that into strings and deal with the cases where we've sent stuff that isn't a string in UTF-8. And then it's up to us to look for lines of text in that data that's coming in. So we have to search for the new lines in that so that we know when we've got a full line of text. Okay? So that's what accumulated lines does. It's not important how it works. It's just looking for telnet end of lines. And then when we get a full line of text, it ends up in this handle function. And this is a bit interesting. We're expecting, so when we start the chat room, the very first thing we do is ask the user for their username when they connect. And so we're expecting that the very first line of text they type in is their username, right? That's how we ask them for their username. So if the username is none, then line is the username. We also have some commands in the chat room so we can list who's in the chat room. In all other cases, we just broadcast whatever they've sent. So this is all, it's actually a pretty straightforward thing. I'll just give you a quick demo. In the last few minutes here. So this is exactly the same, you see that there? This is exactly the same code that I've just, actually no, that's the wrong code. This is the right code. This is exactly the code that I have just shown you for the chat room class and the Async IO protocol class that implements these three callbacks: connection made, data received, and connection lost. So I will run the callback version of this. That's now running, it's waiting for some connections. So if I go here, I should be able to telnet, put it there. And you can see that I've got welcome to Chatterbox, the callback-based version, into your username, Sheila. And then I'll make another connection over here, Jim. And you can see the thing working quite pretty much as you would expect here. So, hi Sheila. Hi Jim. So it's it's just a chat server and it works, and we can put in the commands to list who's in the room, and it's a very, very simple thing. Okay, so that all works fine. Then if I do control square bracket, quit, close my telnet connection, and then we get the user departed, because that third callback is being called, the connection is being closed. Okay, so it's a very straightforward thing. So that's Async IO actually being used for something simple but not entirely trivial. So that was callback based, even though it was using Async IO. So that chat server didn't actually implement any coroutines. All the coroutine stuff is happening in the Async IO machinery. Its coroutines are calling back my regular functions in the protocol. Okay? But of course, there are problems with callback-based programming. I mean, has anyone ever ended up with code that looks like this? You end up with the triangle of doom with your kind of repeated callbacks and the white space there on the left. And what coroutines and await allow us to do is to transform code like this, which is horrible, into code like this, which is really nice. Okay? It's much easier to understand what's going on. It's much easier to understand how data is being threaded through the system. Okay? And these are almost they are exactly equivalent. So I would much prefer to program in this style than that style. Does anyone prefer that style? No. So in the program I just showed you, the state control of when users enter the chat room and when they leave, and getting the first line they send to us and using that as the username, and then treating all subsequent lines differently, is a little bit awkward how you have to program that. And also it's a little bit awkward the fact that we have to find the lines, the logical lines of text in the byte data that we're getting from the transport. So all that code was written at the protocol level, which is callback based. I'm going to show you the same chat server written in a coroutine-based style using the Streams API now. So it's exactly functionally, it's so functionally equivalent that the two chat servers will talk to each other in the different versions of them. So it's very similar code at this level. The chat room has an event loop. Now, rather than mapping usernames to transports, we map usernames to streams. We have a write stream and a read stream corresponding to each user, which allows us to read and write from that user. We create we call start server, which creates a TCP server object. This time, we have to pass a callback here, client connected, which must be a coroutine. We'll see that in a moment. And it will call that coroutine once per user. So here's client connected, and I think this is really significant compared to the previous code. Client connected shows you the entire history of what happens to a user for the entire duration of their interaction with the chat room. Okay, what happens? We say, welcome to the chat room. We await user registration. Okay, so we just sit there spinning, waiting. There's an interesting thing I've discovered here about naming. Generally, I like to name my methods with verbs, right? I've discovered I need to name my coroutines differently, because you don't await verbs, you await nouns, right? So this is an open topic of research as far as I'm concerned, is how we name coroutines, right? You know, we don't do them, we await them, right? So I've found that calling my coroutines things like user registration, which is an event that's happened, makes the code read much more nicely. So registered user await user registration. If registered user, because that may fail, I mean the connection may close and they may disappear. If the user is registered, announce that the user has arrived, which happens here, we just broadcast user arrived. Then await user activity. Okay, so that's all the other things the user could type in while they're going. I'll show you that in a moment. Then when they finish being active, deregister the user, and then we just need to clean up at the end to drain any streams that are stuff in them. Okay, so that shows you that coroutine is executed exactly once per user, per session, right? So there's no callbacks, it's just a single thread of execution that you can trace through, which I think is really nice, compared to the callback thing where you're never quite sure what's going to happen, right? So you could put a breakpoint in here and you can just, as the user progresses through. So it's really interesting. We don't need a separate protocol class now, so everything's in here. So when we await user registration, we're just waiting for some data. We can call readLine on the stream, so the stream does finding lines for us now rather than us having to do it. We decode the data into UTF-8. We strip whatever string we get to get a username, and we register the user. When we are awaiting user activity, we basically have the same code here. And when we get a line, we interpret the line. This is our opportunity to interpret the commands, like listing users, or just sending whatever text it is as a message. So it's even more straightforward at this level. It's a very simple thing. So I think that's the entirety of the chat server. I'm sure you believe me, but in the remaining few minutes, I'll demo that again. So we'll stop that version of we'll stop the callback version and run the streams-based version. So that's now running. So now we should be able to telnet again. Fred, Sheila, where's Jim? So, everything just works as you would expect, right? So, works in exactly the same way. So, I'll just run it again. So, I guess there's quite a lot to get to grips with. Let me just go back to my slides here. So, particularly at this level, there's a lot going on, right? Below that stream stuff, that's sitting on top of the protocols, which I used earlier. That's sitting on top of transports. That's sitting on top of the event loop. That's also sitting on top of generators. So you can get some pretty deep call stacks going on here when things go wrong. And I have found that you do need to understand quite a lot of what's going on below you in order to fix things when things aren't going wrong. So in your own investigations of Async IO, I would advocate basically following a path that you start with the stuff at the bottom here and work up and build your understanding of the higher levels of abstraction rather than trying to start at the top level, because that will go well until it stops going well, and then it will become quite tricky. So try to build up through this lot. So I have 2 minutes remaining, which is just enough for me to say thank you for listening and asking lots of really great questions.